Hello, everyone. My name is Moataz Sheha. I'm a postdoc at MIT Energy Initiative. And the title for today's talk is Modeling of a Flexible Carbon Capture Equipped Power Plant Integrated with Line-Based Direct Air Capture. This is part of a project in collaboration between MIT Energy Initiative and AIChE Capital, a North Carolina-based company. And we do actually have the project manager from AIChE here with us, Philip Cross. So thank you, Philip, for being here. And this project is funded by ARPA-E as a part of their Flexible Carbon Capture and Storage program. And from that comes a background and motivation for our project. So with the increasing penetration of variable renewable energy resources on the grid, this would require more flexible CCS technologies that should be integrated on the grid to allow for the flexible operation of the grid. So here we propose a concept that combines a CCS plant with direct air capture so that we can address the dual challenge of lower carbon emissions while providing the grid flexibility. And we're showing here an example of one of the world's first power plant with CCS that's actually it's not flexible enough, which is a boundary temp plant. And we're showing here a schematic of the direct air capture system, and we will talk about this later on. So in this talk, we will it will be divided in two parts. First, we will go through a process description, and then we will talk about some of the challenges that we have seen during developing the process simulation for this project. So first thing, we have a natural gas combined cycle power plant, where basically a traditional one, you have fuel and air going in, and you would have flue gas coming out, and you will be generating some power that goes for export. The flue gas will go to what we call a calcium looping system that has two reactors, a calciner and a carbonator, and a heat recovery system. And you also have calcium carbonate going into this system that will be break down into calcium oxide and CO2. So you will have the CO2-rich gas. This CO2-rich gas will go to a separation system that consists of a membrane package and a cryogenic purification unit. And we will not go into details of this separation system, but here's it. So the product comes out of that is liquid CO2 at high pressure, and we have some vent gas, and this requires some power that we can get from the NGC power plant. And for the solids part of this thing, it goes to the direct air capture system. So it's a line-based direct air capture. We have calcium oxide as the adsorbent. You will have beds of calcium oxide, and it will be absorbing CO2 from air. And then you will have calcium carbonate as a product. It can be either recycled to the process, or it can be stored. So this can be operated at any power plant loading level, basically. So this power plant, if you decrease the loading from 100% down to any percentage, it can be this system can operate flexibly. You can even turn off the power plant, and this system will still be running because it's not only dependent on the flue gas, it's also dependent on the calcium carbonate. So as long as you keep feeding it calcium carbonate, the system will be running. So that's where the flexibility of this system comes from. And so we have seen that at all power plant loading levels, we can achieve negative emissions. So how do we do that? So you can see we have two sources of emissions here. We have the vent gas from this system and the vent gas from this system. This one almost has no CO2. We're assuming that most of the CO2 is getting captured in the carbonator. But in the separation system, you will have some CO2 going out with the vent gas. But then you have the direct air capture. So on the direct air capture, you have to capture much more CO2 than the ones that you're releasing here. So in this case, you will achieve negative emissions at all loadings. And we have developed this process simulation in Aspen Plus, and this is just a schematic showing how does the system look like in Aspen Plus. We're not going into details here, but we have here the calciner, the carbonator, heat recovery steam generator system, and we have the membrane package and the cryogenic purification units. Then the second part of this talk is about the challenges that we have seen during developing the process simulation. So there are three things. We'll talk about the calcium looping operation, the NGCC power plant operation, and the operation of the capture plant at part loading. So first thing, let's start with the calcium looping system. So there is a lot going on here. We have the calciner and we have the carbonator. So I want to talk about three main things here. You have the flue gas coming in from the NGCC plant. It can go into two places. It can go to the calciner or the carbonator. So we have here a fraction. This is the flue gas fraction going to the calciner. We're calling it alpha. And then you have also the fresh calcium carbonate, which gets combined with some recycled solids. It goes to the calciner. And then out of the calciner, you have calcium oxide. So the reactions happening here, you're combusting natural gas, and you're breaking down the calcium carbonate into calcium oxide and CO2. The CO2 goes out here in this CO2-rich gas stream that goes to the separation system. And then the calcium oxide is either recycled to the carbonator or it can be exported to the direct air capture system. So we have also here another split fraction, beta, which is basically the CO2 fraction going to the carbonator. So two of the main questions here, how much flue gas should go to the calciner and the carbonator, and how much calcium oxide should be recycled or go to the DAC system. So we'll talk about this in the next slides. Another thing here is the conversions in the reactor. So in the calciner, we're assuming that this goes to completion. So of course, the combustion reaction goes to completion. The calcium carbonate reaction, it has almost around 99% conversion. But the story is different with the carbonator. So as you increase the recycle amount, the conversion will decrease in the carbonator. So that's what we're going to talk about now. So the carbonator conversion. So on this figure here, on the x-axis, you have the number of cycles, like how many cycles you're recycling your solids. And on the y-axis, you have the conversion and the particle fraction. So this curve here is showing the conversion. And you see as you increase the number of cycles, you're decreasing the conversion until you reach a residual conversion at infinite number of cycles. This conversion here is 25%. But how many particles are reacting with this conversion at each cycle? So here is another curve that shows at a value of beta as a split fraction of calcium oxide of half. So in the first cycle, you're recycling 50%, beta is equal half. And then you're getting 50% as a fresh feed. So 50% of the particles will be reacting with the maximum conversion. And then in the second cycle, it would be 50% of the 50%. So it will be 25% reacting with this lower conversion, and so on. But then at the end of the day, this is a profile of conversion. We need only one value to put in the simulation. So at each value of beta, we just need one value. So if you do the math around this system without going into too much details, you can end up having this curve. So you can go on the x-axis with the split fraction, and then on the y-axis, you have the average calcium oxide conversion in the carbonator. So for our system, right now we're using, for the base case, we're using a split fraction of 0.5. This corresponds to around 65% conversion of calcium oxide. And then the second thing that we want to talk about is the split fractions, the amount of flue gas going to the calciner, and the split fraction for calcium oxide, the amount of calcium oxide being recycled to the carbonator. So to remind you, how does this look like? So we're talking about alpha and beta here. So if you can see on this figure, we have on the x-axis alpha, the flue gas fraction to the calciner, and on each curve, it has a constant value for beta. And then on the y-axis, we have the CO2 mole fraction before the membrane. So we care about the concentration of CO2 in this stream going to the separation system, because the higher CO2 concentration, the easier the separation will be, and the lower the energy requirement for separation. So if you can look here, if you look at this curve, for example, at a constant value for beta of 0.9, as you increase the amount of flue gas going to the calciner, you are decreasing the concentration of CO2 before the membrane. So this is not favored. This means that we need to stick in this region here. You should send as minimal amount of flue gas to the calciner as possible. And then if you look at it from a different way, you can, for example, look at a value of 0.4 for the calciner, and then you look at this vertical line. As you go down, you're increasing the value of beta. So as you increase the recycle, you're decreasing also the concentration of the CO2 before the membrane. So it means that as you increase the recycle, you're decreasing the conversion, you're decreasing the amount of calcium carbonate going to the calciner, you're decreasing the CO2 going into this system. That's why you're decreasing the concentration. So this is not favored. Another thing that we should consider here is that as you increase the amount of calcium oxide being fed to the carbonator, this means that you increase the carbonator size, which increases the capital cost. But as you also increase the amount of recycle, means that you're decreasing the fresh feed. So you'll be decreasing the operating cost. So you can see here that we need to have an optimization problem and solve it to identify the values of those variables. And for our base case, we use the value of 0.2 for alpha and 0.5 for beta, as we have said, and the conversion is 0.65. And then for the natural gas combined cycle power plant, this is a schematic of how the power plant look like. It's a traditional NGCC power plant. You have the combustor, you have an air compressor, then you will have the flue gas going to a gas turbine, you're generating power, and then you go to a HRSG system, heat recovery steam generator, you're also generating pool power here, and then the flue gas goes to the capture plant. This plant at full loading, it has 727 megawatt net, and then at part loading, three things happen at part loading. The flow rate of air and fuel decrease, and the air-to-fuel ratio increase, and you're decreasing the pressure in the discharge from the air compressor. And we have here on this curve the efficiency of the plant. So you start with 100% loading at around 54% efficiency. And as you go down in the loading till 40%, you reach around 42% efficiency. We think that this should be the minimum operating level of the power plant, 40%. If you go below that, it's better to turn it off because the efficiency will go down a lot. So this was for the NGCC plant. What about the capture plant? So for the capture plant, we have said that it's dependent also on the calcium carbonate. So to remind you what we're talking about here, so the fresh calcium carbonate here. So at part loading, the flue gas will decrease. This one is coming from the NGCC plant, so it will decrease. But what happens to the calcium carbonate, the limestone? So you can either keep it constant at the full loading value, or you can scale it down as you decrease the flue gas flow rate. So how does this affect the system? So if you can see here on this figure, on this heat map, we have the power plant loading on the x-axis, and we have the limestone feed on the y-axis. And then we have this heat map for the power required for the capture system. So if you will decrease the limestone feed, basically you're scaling down the system as you decrease the flue gas flow rate, the energy requirements will decrease. So that makes sense. But if you keep it constant at any value, and while you're decreasing the loading, the power requirements will increase. So this also makes sense. So it's if you're decreasing the limestone feed, it makes sense that you will be decreasing the power requirements. If you're keeping constant, the power requirements will increase. So this makes sense here. And if you're keeping it constant, the excess calcium oxide, you will have to change the value of beta in this case and export the rest of that to the direct air capture system. So this might also have implications on the direct air capture systems that should be studied as well. And so the takeaways message from this is that the proposed power plant concept, as we have seen, it can be flexibly operated. You can turn off the power plant and the system would be still running. And it has potential to achieve negative emissions, as we have said. And as you have seen that we have some parameters that we need to optimize. So for this system, we need to perform an economic optimization under time varying electricity prices so that we can use it to identify the optimal design of an operation for the system. And that was the last thing that I have. Thank you, and I'll be glad to take your questions.